right, good morning everyone. So, actually before we start, some snacks there, drinks there, please help yourself. Hopefully you brought some as well. It's just I forgot to mention yesterday, but we usually just bring snacks and stuff on Friday, because it's Friday. All right, cool. So today we're going to be working on gradient descent and weighted knit in the morning, and then we'll be discussing in the afternoon another set of slides, which is just talking through some of the more practical parts of actually doing a neural network, right? So how to deal with things like underfitting, overfitting, how to actually work with loss curves, that sort of stuff. So a lot to sort of cover today. So let's just get started on gradient descent. So yesterday we obviously talked about how neural networks worked, how backpropagation works, so sort of the background of how all this stuff works. And then we also discussed the different types of activation functions that you could have at the different nodes of the neural network, as well as different loss functions depending on what outcome you want to measure for. And so as we sort of covered for the activation functions and the loss functions, for example, the last layer of the neural network, right, and the loss function usually just match whatever output you want, right? So if it's like binary, then you need sort of a binary layer and a binary loss function, right? If it's multi-class, then you need softmax, right, for the final layer as well as the loss function. And then if it's like continuous output, then you sort of want a linear layer at the end, and then mean squared error as your loss, okay? So sort of just, again, wrapping your head around those concepts. And then for the activation functions themselves in the neural network, what we were basically looking for was a non-linearity, right? So something that's just non-linear. The simplest one that we have is just a ReLU function. And if you sort of think about it, you can actually construct any function using the ReLU function, right? So for example, I mean, maybe something janky, like if you have a quadratic thing, that's like a ReLU there and a ReLU there, right? It's a sort of an approximation, right? And so you can sort of, again, construct anything with ReLU. So it's pretty cool. And it's actually a proven sort of mathematical thing where you can actually build anything with the ReLU function, right? And that's sort of why neural networks are so powerful, because we can then model any relation we want. Okay, so it's sort of very cool stuff. We also talked about JLU. So JLU is a very word-specific thing, a very transformer-specific thing, and like we were seeing in the Cahoots, just that little sort of curves, right, would allow nuance to get through really big models, okay? And so that's like how AI engineers think these days, which is you almost look at the math function, you graph it out, and you're like, yeah, the words can get through that part near the origin, right? Like it's sort of weird if you think about it, right? But that's sort of how we think about some of these functions. Now let's talk a little bit more about gradient descent. So far, just to sort of recap on what gradient descent is, it's just this algorithm where we consider our current position, we find the direction of the steepest negative gradient, and then we take a step, right? And there's always math behind it, that sort of thing. You can always dig into the math if you're interested, but what's sort of important to take away is the intuition, right? And the best intuition I found is just imagining yourself on a landscape, right? And you're standing at some random point because you've been randomly teleported into this landscape, right? So that's random init. And then you're actually just looking for the downhill, and then you just walk downhill, right? And so that's what this gradient descent algorithm basically does, okay? And so once you find the downhill, and as you can see these sort of three dots here, they're completely random init, right? So sometimes you might be really unlucky and you end up here, right? And higher basically means more error, right? So it's a bad thing to have. But sometimes you might random init in these two parts and you end up nicely here, okay? And so even yesterday when you were trying on a very small neural network, really dummy data even, some of you found this, right? It was pretty obvious you had found this, and then some of you had found this, right? Like you had a lot of error, and I was walking around seeing some people get really low errors, and then some people just completely because of random init, they were ending up here, and they were thinking that that was the best algorithm that they had. So sort of funny. So again, that's just gradient descent, right? You're just trying to find the value. That's all it is. So what we've talked about so far is a process called vanilla or batch gradient descent, right? Which is the original one that we created, right? And basically what it means is that we go through in every epoch the entire data set, right? So epoch by definition means that you go through each data point in your data set once. Okay, that's just what epoch means. But in the sort of situation or in the method that we currently have, we process the whole data set in one shot. Okay? Now that works quite well for small data sets, right? So when you have small data sets, no big deal, right? You're just processing the whole lot. But imagine if you have the entire corpus of the internet, right? Which is what some of these models are now trained on. It isn't as simple, right? Like how do you process the entirety of the internet in one shot, okay? And so it becomes a bit of a computational challenge, right? And so as data sets get bigger and bigger, vanilla and batch gradient descent get more inefficient, right? Because you're processing huge amounts of data, right? Like potentially even trillions of gigs or whatever. And so if we import all data once every cycle, this gets very, very slow with large data sets, right? And so people were like, can we do better with this? Because as data sets are growing, this becomes a very inefficient method. And so what people came up with was, and I think this was about 10 years ago, was a method called stochastic gradient descent. And basically, at any sort of run, you're basically selecting a random data point. So you just select a random data point from your data set, and then you train just on that data point, okay? So sort of a very interesting idea. Now, gradient descent, you know, when you sort of batch the whole thing, it looks very smooth, right? So this is what the sort of convergence looks like. With stochastic, because you're getting a single data point, it's very noisy, right? Like you don't know if that was a good data point or a bad one, you don't know, right? So it sort of jumps around a little bit. And so stochastic gradient descent actually sort of jumps around like this, right? But in aggregate, because ultimately you're gonna process every data point anyway, right? Like sort of if you randomize long enough, right? Sometimes you might get the same one twice and you've never even touched the other one, right? But at some point, you'll probably hit most of them, right? And so in aggregate, it still sort of leads to the same level of convergence. It's just really noisy when you look at it, okay? So it's a little bit like you, I don't know, like in the landscape, you just sort of jumping around, but you're still making your way downhill, right? And the sort of advantage of this is it's a lot faster. It's a lot faster, right? It looks really noisy, but it's very efficient, right? So it sort of gets to the value very quickly. Now this is also great for a paradigm called online learning, right? Which is if you imagine, you know, you're running like an online website or something, you're getting new data constantly, right? And you're learning from that data constantly. So that's called online learning. So offline learning is what we've done so far, which is we have like a sheet, right? Like a Google sheet, and we're just using that data offline. We're not connected to anything, right? But if you're running a website, you're getting new data constantly, you're learning from it, right? That's called online learning. So online learning is really great for this because you don't get batches of data at once, right? You get data, you know, one at a time, right? Just every time a user might click on your website or something, you're trying to learn from it, right? That's a single data point you can train on, and then you just keep on going, right? So that convergence sort of happens in a very noisy way. Now, people realized that stochastic gradient descent, very noisy, but it was sort of computationally a bit of a waste because you're using, you know, the GPU, the expensive GPU that you've bought on a single data point every single time, right? And so they came up with something in between called mini batch gradient descent, which is a middle ground between batch gradient descent, that's BGD, and stochastic gradient descent, right? And so mini batch is the current gold standard. That's what just people use. And it basically updates with a random mini batch, so of 32 to 64 samples. And why 32 or 64? It's just whatever fits on your GPU, right? So the GPU has, you know, a working memory that it can store some stuff, and so you just fit whatever the GPU can store, right? So it's more of a practical number. And so conceptually, again, just thinking about what that actually looks like in this landscape that we have, this is what batch gradient descent looks like, right? This is our stochastic gradient descent, so very, very noisy. And then mini batch is sort of in between, right? Because it's conceptually in between. So it's less noisy than stochastic, it's more noisy than batch, but it's very efficient in getting to the central point. Okay, so that's mini batch gradient descent. Any questions about that? Yeah.
For the stochastic one, does it mean like if you randomly jump to another place and then you reach to the bottom, or?
Yeah, so you see how it sort of jumps in all sort of weird and wonderful directions, but in aggregate, your vector is still heading towards the convergence, right? Yeah. Other questions? Okay, hopefully conceptually pretty easy. You know, so you have batch on one end, stochastic on the other, and we're sort of in the middle, right? And that's what people currently use. And part of that reason is obviously because we have, you know, the internet to train on, and so we need to be quite efficient with it. And most of that internet is already sort of available right now to us, right? And you sort of see it in batches a little bit. Okay, now other ideas that came up, and some of these ideas are really sort of critical to gradient descent. Gradient descent by itself is not actually that great. So it's not the most efficient way of doing things. And so, I think people with physics background sort of looked at this and were like, what if we consider our previous step, right? And they called this momentum, right? And so momentum is a method that is quite cool. And basically it just smooths out the trajectory, right? By counting the direction of our previous steps. So it says we've taken these steps, right? Like, so I'm sort of walking this landscape, but we're not considering what's happened behind us, right? We haven't considered like the steps that we've taken just right before, right? But we should, right? Like if you're walking downhill, like you sort of think about where you've come from, right? Like not like you're just considering every step by itself, right? And so momentum takes into account the direction that you previously were moving in as well, right? So say for example, I know I'm just like walking this way and then I walk this way, right? If I'm at this step, I know I've just walked this way, and so I'm gonna walk somewhere in between, right? Because I know that roughly looks like downhill. Okay, so that's actually just the concept of momentum. And so this is what stochastic gradient descent without momentum looks like, and then with momentum. And so as you can see, it's not like a sort of silver bullet where you solve everything, but it is smoother, right? And it's a bit more efficient, right? And so it does actually improve efficiency. Now with momentum, there is this, this momentum coefficient that we call beta, right? And again, there's no science to it. There's no like fundamental reason. I was teaching a bunch of like, clinician PhDs on this, and they wanted to know like why, it's 0.9 or 0.99, right? Expecting almost like a biological reason, right? But someone just tried it and it worked, okay? And so the answer is everyone just uses, like they literally try these two numbers for the beta or momentum coefficient and then just see which one does better, right? And then you just stick with that one, okay? Yeah, what exactly does it mean? So I think the momentum coefficient is how much you're considering momentum, right? So how much of a factor it actually plays in walking downhill, right? And so 0.9 or 0.99 means that you consider momentum quite a lot, okay? So 0 would mean that you don't consider momentum at all, and 1 meaning that you consider momentum almost fully, right? And so 0.9, 0.99, that information just means that, or that number just means that that information is quite important, right? For most models, okay? So that's momentum. And so I don't talk about how it can be, it's actually going to be in the exercise, you're going to implement momentum, but it's really simple. It's just a single line. You need to just add in like an argument, and then you can sort of get it working, right? So quite straightforward. Nesterov momentum. So this is another type of momentum that instead of using information from the past, it uses information from the future, right? So it basically says, you've traveled in this direction, you should look ahead in the direction that you're traveling in, and then take an average, right? So again, sort of a different idea. So this is a regular momentum update, and this is Nesterov momentum, right? So in regular momentum, say you previously stepped this way, and now you're stepping this way, right? So the gradient, you basically just correct, right? And sort of take an average there. For Nesterov momentum, this is your actual step, this is your momentum step, and so you'd correct sort of in the middle there, right? It's just slightly different, so instead of using information from the past, you're using information from the future, right? Now, Nesterov momentum is something that you might see around. People don't use it as much because it's computationally expensive, okay? But I have seen actually like maybe 40% of papers you'll see Nesterov momentum, around 60 use momentum. So it's just something to be aware of. Conceptually, to me, they feel a little bit the same. I think performance-wise, Nesterov is a little bit better, but computationally it's a lot more expensive. So people sort of sometimes just stray away from it because it can get quite expensive. Okay, now that's momentum. Now another idea that was floated was called adaptive gradient, and actually someone I think was talking to me about this yesterday. They were like, why can't we just do this? And I was like, this is actually a thing. So each weight has its own learning rate. So someone was just like, what if each weight just has its own learning rate? So what does that even mean? It basically means that, say we have a two-dimensional landscape, right? I actually calculate the downhill on one axis and then the downhill on the other axis, and then I take the sort of average of the two, right? So I'm considering like the step size for each individual axis. Does that make sense? So instead of sort of looking at the landscape as a whole, I'm like, okay, this one here, like this axis here, is really downhill, right? So I'm going to take a huge step in this direction. This one here, it's sort of uphill or like slightly uphill or whatever. So I'm going to take a small step in that axis. Does that make sense? So again, it's just sort of mathematical tricks to get the gradient or the learning rate to be a lot more smart, right? And so yeah, so that's adaptive gradient. Now what people actually use is not AdaGrad anymore, but they use this thing called RMS prop, right? And part of the reason is that with lots of data, the learning rate for AdaGrad becomes ultra small for some parameters, right? Because you sort of hit like a, like a flat area, right? And then sometimes the landscape just sort of looks flat for quite some time before there's a valley actually in the distance there, right? And so RMS prop basically just solves that with some mathematical tricks so that you don't get stuck on a flat plane, right? On some of the axes. Okay, so again, just mathematical tricks. It's more just rather being aware that these exist, right? You can always look up these if you need to, right? But these are sort of standard stuff. If you ever read any good AI papers, you'll always see constantly, right? People will just be like, yeah, we use RMS prop, we use momentum, right? So it's just knowing what sort of roughly they mean. Okay, so people realized after a few years that momentum and RMS prop is ultra powerful, like just the combination, right? So someone came up with a name for it, which is called Atom. And I think it's literally just, they named it after themselves, right? Right, Atom. So yeah, combines momentum and RMS prop, right? And this is this sort of gold standard right now. So everyone uses Atom, right? So if you see any paper, you see Atom, it just means that yeah. And it's great because he didn't invent momentum or RMS prop, right? But he managed to get his name in there because he combined the two. I don't know. It's pretty cool. And so again, this just creates sort of free variables here. The learning rate is free e -4, so that's 3 times 10 to the power of -4, right? That's what that means. And then there's two variables, beta 1 and beta 2. And again, it's just related to how much momentum you want to sort of add. And so beta 1 is always 0.9 and beta 2 is always 0.999. Why does it work that way? I don't know. Someone tried it. They really liked it. It always worked. And so everyone just picked up on it, right? Atom W is a much more stable version, which everyone now uses. So Atom W, when you see Atom, usually people actually mean Atom W because Atom W is the gold standard. And yeah, it's sort of, I don't know why, but like there was like a whole set of memes related to this number, right? So 3 and -4. So if you sort of dig enough into the AI community, there's like whole fights about like, should you do 3e -4 or like 5e -5 or whatever, right? So anyway, 3e -4 has 1. So everyone just uses these numbers now for transformers. So it's sort of very interesting, okay? All right, any questions before we move on to sort of more complex stuff? No? Okay. All right, the final sort of idea, I believe it's the final one, yeah. The final sort of idea that has come up recently is something called a learning rate decay, which is that you start with a certain learning rate, and then you actually let it decay over time, right? And then you let it pop back up, and then you let it decay again. So what does that even mean? Like conceptually, I guess it means that you're taking huge steps initially, and then you sort of take smaller steps, and then you suddenly take a huge step again, and then take smaller steps. And for some reason, like even just that sinusoidal sort of nature means that it's a lot more efficient. I really don't know why, right? It's sort of an unusual thing to see. And so the gold standard is Atom W, right? Which is that optimized version of Atom, which is momentum, momentum plus RMS prop, right? And then you add this thing called cosine annealing, which basically just means that you have a decay here. That's called annealing, right? So that's called annealing. And then in a cosine way, right? With warm restarts, which is you sort of restart every single time. So again, it's not something that you ever need to mathematically put out yourself. It's literally just one line in code, but it's just being aware that that function exists, and then you can use that, and for some reason it will make your AI models better, okay? Yeah, so sort of unusual. All right, so that's gradient descent, right? So the sort of three keywords there is momentum, RMS prop, Atom W, right? So Atom W is the sort of gold standard, and then cosine annealing with warm restarts, Okay, the next topic is weight initialization. So, what happens if we try and zero init, right? So we talked about random init yesterday, but initially for 10 years or so, people actually did zero initialization, right? Which is instead of randomly, initializing every weight, so it's like randomly selected number, they would just say let's just start with 0, right? Now, the only problem with this is that all weights are essentially updated the same amount. So when you back pop through this, all the weights basically update the same amount, right? And so it leads to a bit of a symmetry problem where the relation that the neural network is modeling has to be a symmetrical function, right? Which is not what you want, right? A lot of functions aren't always symmetrical, right? So zero init wasn't a great choice. We then moved to random initialization, which is actually what you all have been doing now. It breaks the symmetry, but it doesn't work well for large neural networks, right? And part of the reason why is that large weights, for example here, will tend to explode, right? So they tend to actually explode upwards towards infinity. And then small weights will tend to vanish towards 0, okay? So what we've taught you so far isn't actually the most efficient way to init neural networks, but it's something that's easy to understand initially, right? But no one ever really does it in real life. Okay, so the best practice is to draw from a normal distribution, right? So you basically just don't want too large numbers. You don't want too many small numbers as well. And so we just use a normal distribution. And again, is there a logic to it? Not necessarily. Someone just tried it and it worked well, okay? And so we draw from a normal distribution, and it's funny because the mean's at 0, which means that some weights will eventually vanish, right? Because it's close to 0, that's fine. And the standard deviation is this number here. And I have no idea why. There might be some mathematical reason for it. I don't even know it, right? Like I don't even need to know it. And so there are two types of initialization. One is called Gloro initialization, or the full name is actually Xavier Gloro. So it's a French researcher who found it, right? And so you might see Xavier init or Gloro init. It means the same thing. And then there's another type of init called he init or Kaiming init, and it's just a guy named Kaiming he, right? And so people unfortunately just call it different things. It's either Kaiming init or he init, but it refers to the exact same thing, okay? And basically we've just found that for hidden layers, you should use Kaiming he init, and for output layers, you should use Xavier Gloro init. And for some reason that works really, really well, okay? Yeah. So again, this sort of exists in code, right? And so this is the code that you need to use, right? So this is for the hidden layer here, you just use Kaiming init, and then for the output layer, you just use Xavier init, and it works really well. Okay? Yeah.
Just a question, like, there's all these like empirical things that I found too.
Yes.
And like, are there any like theories like that connect any of them together?
No.
Like,
Absolutely not. Yeah. Yeah.
Well, with the standard deviation, it's like square root 1 on n to n.
Yeah.
What's n? Is n just the number of training samples you have or something, or what's n?
I think n's the number of training samples, but you might need to double check actually. I haven't seen this. Sorry?
It go to 0, right?
Yeah. It can't go to 0, right? Yeah.
Yes.
Yeah. I mean, if it goes to 0, then it breaks. Yeah, I think it's the number of training samples, but double check. I really can't remember actually. Yeah. Yeah. Yeah, I mean, as you can see, the AI field is, I guess it's because it's not like a biological thing where it's like there's risk of harming a patient or something, right? It's just like someone tries a thing in code and then it works, right? And there's no harm if it goes wrong. Yeah, so sort of very interesting to see. Okay, so actually to summarize, so this is the last slide of at least this set of slides. This is what the state of the art looks like right now if you're going to train a neural network, right? So maybe take a picture of this, I don't know, like just every time you run an AI function, just make sure you have all of these, right? It just means that you have what is best practice, right? And so I'll let you take a picture of that and then we can just almost summarize or go through it, revise it again. So, activation function. We want ReLU for neural networks and JLU for transformers, okay, for the hidden layers. For the output layer, we want linear, binary, or softmax, depending on what we need for the output. So that actually depends on your use case. There's no right or wrong for that. Loss function is the same. So mean squared error is for continuous, binary cross entropy is for binary outputs, and then softmax cross entropy is for multi-class outputs, okay? Gradient descent. You want to use mini batch gradient descent with atom W as your momentum sort of optimizer there. Those are the variables you want to use. So a learning rate of 3e minus 4. So you know how you might have tried like 0.1, 0.001, whatever. It's actually easy because you should just do this and no one's going to fire you, right? Beta 1 is 0.9, beta 2 is 0.999. What does that even mean? It's basically a metric of how much momentum you're considering in the equation, right? And so they're just literally variables that you just put in the function. And I think the default is actually these as well, so you might not even be able to need to do it. Add in cosine annealing with warm restarts. That's a single function in PyTorch. And then for weight init, for the hidden layers, you should use he or Kaiming init. And then for output layers, you should use Gora or Xavier init. Okay? That's it. That's like best practice. So a lot of papers in software engineering will have this. A lot of papers, or very few papers in medicine will have this. Okay? So it's just because people who work in medical AI don't know this. Okay? Yeah. Cool. Yeah.
They don't know it, or as in they use like older techniques.
Yeah.
Oh,
Yeah. Yeah, so they'll use older, like for example, they might use like stochastic gradient. Like if you see stochastic gradient descent, right? So I mean, this list is also useful for you to tell the quality of a paper, right? Because if they're using like, you know, if they're using the wrong any one of these, then it's catastrophic because they're going to get the wrong output anyway. If they're using like stochastic gradient descent, then you know that the team is not quite as updated as, you know, most other people, right? Or they don't use cosine annealing, right? Like they don't even mention this, or they're using momentum instead of atom W, right? Like, so you can also use this list to sort of see how good the team is, right? Yeah. Oh, sorry, one of you two.
Like, why do you think that is? Like, is it because they like? Because usually teams who work in medical AI, they do have like at least some like
Yeah.
AI engineering input.
Yes.
Like, if they're AI engineers, why wouldn't they be caught up? I guess is it like?
It's harder to catch up than you think. Yeah, there's just like there's no central body that's like, hey, you know, this is the best list here. Like I only know this because I read a lot, right? Like I spend a lot of time reading stuff, and so, you know what comes up, right? But if they're busy and, you know, the job's a full-time job, like when do they have time to read this, right, and figure it out? Yeah. Even like I was presenting at a lab the other day. It's like one of the best medical AI labs, right? And yeah, like even this stuff is, it's like, yeah, like this stuff is really critical just to sort of get the best models, right? Yeah. Yeah.
I was going to ask what the best way is to keep up to date.
Yeah, that's a great question. I actually don't know if I have a perfect answer because the field itself is so messy. It's like so. I've heard of Twitter, so some people swear by Twitter. Some people swear by Twitter. Some people swear by Hacker News, right? So I'm maybe one more of the adherents on. It's like a forum founded by like a startup incubator in the Bay Area called Y Combinator, which is like the top one. They did like Airbnb and Reddit and like all the big names, right? Yeah, so sometimes like you'll see stuff on there, but you have to sort of know what you're looking at, right? Like if someone's like, oh, like cosine annealing is better than you know, some other thing. It's like, if you don't even know what cosine annealing is, you have no idea at the article you're seeing, if that makes sense, right? And so this is also designed to kickstart your knowledge and for you to be able to keep up, right? Because at least you know what those terms are roughly now, right? Like, or you know it's important to AI at the very least, right? Because yeah, I imagine like someone might see cosine annealing and think it's related to metals because annealing is a term historically related to cooling metals, right? Yeah, so it's like, yeah, like when I initially heard annealing, I was like, oh, I'm not interested because it's like, you know, as in I'm not that interested in metallurgy, right? But yeah, but then now I realize that's an AI thing, right? So I'll look into that paper because I'm like, okay, there's something new in addition to cosine annealing. And it's also somewhat, yeah, let me just see how else to answer this. Yeah, there's also some courses online which are quite good, but you have to be constantly updating, right? So like later on when you get familiar with transformers, like what we recommend is keeping track of CS25 from Stanford, right? So they update their course about once every 18 months or so, right? And so that's a really good resource to keep up to date about what's happening, right? Another source, weirdly, is Substack. So there's lots of like blogs, like specifically on Substack for some reason, where you can basically keep track of what's happening, right? So one that I read quite often is interconnects.ai. So that one, like, it's just, I don't know, the guy's really tuned into stuff. So I just read, and like sometimes I don't even understand half the stuff he's writing about, but it's like, oh, okay, like there's something interesting happening in this space, right? And there's probably other substacks like that I don't even know about. Yeah, that's a great question. Yeah. Other thoughts? Okay, cool. Yeah, so the next is to go back to this collab that we were working on yesterday, right? And then there's actually an exercise that almost gets you to build a state-of-the-art neural network, right? It's not, you don't have to build a big one. You can be like 2 layers or whatever, but it's rather that it just has all the optimizations you need, right? And so you can again save that code and use it in future or whatever you want, right? On whatever project, and you know that you have a solid neural network, right, to work on. All right, cool.
Like if it changes only once, like the rest.
All right, awesome. Feel free to get some snacks. Feel free to get some drinks, although the pink lady's gone, but we still have a lot of Lipton lemon iced tea. Also brought some American chips. These are really good. Ruffles. I don't know if you've ever had them before. We bought like a Costco size pack. All right, so let's go through the stuff we need to for this afternoon. So we're gonna go through, so now that you sort of know how to build a neural network, right? Like what you have in front of you is actually, it can work for anything, right? Like if you need to do research with a neural network, feel free to use it. The stuff that we're gonna cover next week though is, I think, a lot more exciting. So with projects, you're thinking less this stuff actually and more the stuff that you'll learn in the coming weeks, right? But this forms the backbone of everything else that we're gonna learn, right? And so once you have a neural network, there are a couple things you need to worry about, right? And so this sort of section here will cover some of the stuff you need to be thinking about once you have a neural network that's working, okay? So firstly, we're going to discuss underfitting and overfitting. So we've previously discussed this before, but when you sort of train a neural network, if you haven't trained it enough, then it does something called underfitting, which is it just does really poorly, basically, right? Like it hasn't learned very much from the material that you've given it, and the model is considered underfit when you've just randomed it, right? Or even the first 100 epochs or whatever you might have, right? That's also called bias, right? And I really hate these bias and variance terms because they're a little bit confusing to me, but they're also sort of widely used, in the field, and so you just need to be aware that if you ever see bias and variance, really what it's referring to is underfitting and overfitting, right? And part of the confusion as well is, bias, we use that term as weights and biases, we use it in other contexts as well, so it's a little bit vague as to what you're actually referring to. Now, underfitting is not so much of an issue because the answer is simply to train more. Okay, so just keep on training, you're gonna fix underfitting, okay? Once you sort of train well, then it's just right, and then if you train too much, then you lead to this issue called overfitting, which you've now run into, which is, for example, if you do too many epochs, then you might overfit to the data, or in a regression problem, you have too high a degree for the polynomial equation you have, or you have too many nodes in your neural network. The model is prone to overfitting. And so what overfitting basically means is that the solution learns too well, but only for the data you've provided. Okay? So it's very much that concept of like, hey, like it really perfectly aligns here, but if you provided a new sample, it might do quite poorly. Does that make sense? So a sample it's never seen before. Okay, so overfitting is actually the sort of bane of your life as an AI engineer. Overfitting is a huge issue, right? So actually most teams, they spend a lot of time trying to fix overfitting because a lot of risk comes from overfitting. And so conceptually, what it basically means is like a child or a young medical student or whatever sees a man with an AMI, right? And assumes that only men can have an AMI. So it's sort of that concept, right? Like it overlearns from the data you provided. Okay, so it learns too many rules. So how exactly do we actually solve it? And this green line here is a perfect example of overfitting. You see how it fits so perfectly to the data. It's so correct, but it doesn't really learn the general rules. Okay, so it's a bad thing to have. So the sort of conceptual way to solve this is to encourage the model to focus on the broader underlying patterns in the data rather than specific details or noise, okay? And it's okay, again, you see how this black line, it's not perfect, right? But as humans, we sort of operate on heuristics as well. We're not perfect every single time, and that's okay, right? And so it's the same sort of philosophy with the AI. It's okay if it's wrong sometimes, right? You're never going to get 100% accuracy. But at the same time, when new samples come in, that rule can apply, okay? So intuitively, these are sort of the options that you have. So one, you can simplify the model. So for example, we have too many nodes in our neural network. We can decrease the number of nodes in our neural network, right? So that's simplifying the model. Second is to improve data diversity. So it's not just the model itself. We can actually improve the data we're training it on, okay? And this is a really critical one, particularly for large language models. If, for example, as you can imagine, if you train a transformer solely on English, then it's going to do really well in English, but then do really poorly for French, right? And so providing it French data now improves data diversity, right? And then if you give it more and more languages, then it generalizes across knowledge in all languages. You see? So that's one way to prevent overfitting. The third way is to validate on unseen data. And so we're actually going to talk about this, I think, on the next few slides, where you split your data between a train set and a test set, right? Or a validation set as well, which is a third option. And so there is data that the model doesn't get to see, right? It never gets to see during training, but you test it on that data, right? So it's data that, it's never seen, and so it's not sort of biased towards that data. And then the fourth one is to make the model resilient to noise. So that is, the model sort of ignores some of the noisy things that are happening here, right? Because sometimes, even ground truths, when we're giving it the real answer, we're not 100% right all the time, right? It's like we could label this patient as having pneumonia, but even humans are infallible, right? We might have gotten that pneumonia wrong as well, okay? And so making the model resilient to noise is another sort of big strategy. And so often to deal with overfitting, it's often a mixture of these four. Now, another sort of strategy that has come up as well, and this is a little trick that you might see around, is data augmentation. So, and right now it's become a field called synthetic data, which is, can we make new data from existing data, right? So can we sort of almost hack it a little bit? And so this was really popular when it came to images, right? So images were a big thing from around 2012 to 2018 when we were building these things called convolutional neural nets. And the tricks that people use was that, we have this initial number 3 here. What if we flip it? What if we pad and crop it? What if we rotate it, right? And for some bizarre reason, like if we did that at scale, the model would do better, right? And what it basically meant was that, sometimes when you upload an image of the number 3, it isn't perfectly oriented like this, right? Sometimes it's a little bit off center like this. And so the model can better see that and actually recognize that that's a 3. Does that make sense? And it's the same with chest x-rays. When people were doing chest x-rays a couple of years ago, they would basically, it's pretty funny, but they rotated like 365 degrees, right? And that's like your 365x your data, right? So that's a lot more data. When it comes to language, right? You obviously can't apply things like pad and crop or rotate for language, right? But you can sort of conceptually do it for language a little bit, right? Like not like, like maybe it's like you can use synonyms instead of actual words, right? Like known synonyms from a thesaurus. So like conceptually you're sort of doing something similar, but you need to think about what that actually means for language while you're sort of augmenting the data. Right, data diversity. So again, I keep on talking about this. This is a really important concept to be always thinking about, which is, what data have I trained on and what might I be missing, right? And so what that looks like in a healthcare context is, say I train on Monash Health's data, right? What I might be missing could be that, I'm missing like what rural distributions look like for a certain disease, right? Or might be missing what, I don't know, maybe Sydney might, categorize diseases differently to how we categorize diseases here, right? So that's sort of what you need to be thinking about, which is, can we get data from other sources, from other things that might, represent a slightly different distribution, okay? And so the large language models we have now, they're very American-centric, as you can imagine, because a lot of the data comes from America, right? And it's how Americans perceive things. So even something like football, right? What is football? What do you think ChatGPT thinks football is? Yeah, exactly, right? Is it soccer? Probably not, right? So you always have to be sort of asking this, and when you're dealing with medical AI, this is a really critical question. And it's really hard to answer because it's like, what am I missing, right? Like you're trying to quantify something that doesn't exist, right? Like, or something that if you don't think about it, you'll never see it, right? And so this is a really important question whenever you're dealing with AI. All right, so some basic methods, and just saying that this method here is quite popular for neural networks, but for transformers, we sometimes use it, we sometimes don't. So you see it a little bit less when it comes to some of the newer AI models that have come out. But if you ever deal with neural networks, this is the gold standard, right? So when you're dealing with data, you always split it into training data, so it could be 50%, right? And then 30% is what's called a validation set, and then 20% is the test set. So what you basically do with this one is you train just using gradient descent with this one. And then it used to be that we'd fine tune the model, which is we freeze some of the model, right? So say our model has like 5 layers, we actually freeze the first 4, and then we unfreeze, so keep unfrozen the last one, right? Meaning that when we update our weights, only the last layer is updated. Okay, so that's called fine tuning. So we'd fine tune on this set here, right? So it's just like in the landscape, it's like you've sort of found the valley and you're just moving tiny little steps now towards deeper into the valley, okay? And then you save this 20% as your test set, and so the model never gets to see this or never gets trained on this, but you only test it to see how well the model's doing to unseen data. Okay, so that's called a train validation test split. Very, very common, yeah.
Is there a rationale for
The ratios? No. Yeah. Someone tried 50, 30, 20 or 60, 20, 20, and they're like, yeah, that works. Yeah. Now, something that you might also see, and this is actually considered better practice than train validation tests, is what's called k-fold cross-validation. And so it basically just says, hey, split up your data into a number of folds, right? Usually it's 4 or 5, right? And so let's say it's k just means it's like it's like any number. So 5-fold cross-validation means that you split up your data into 5 folds like that, right? And then you have a test set that is always the test set, okay? So 20% of your data is always this test set, that never changes. But then the red will be train, and then that's validation. And then it actually cycles through. So then this becomes train, and that becomes validation. And then that becomes train, and then that becomes validation. So you actually take turns being the validation set. Does that make sense? And then for some reason that works a lot better than train test validation by itself. Okay? So you just see k-fold around. Any questions on that one? Yeah.
Can you elaborate on the nature of validation? So we use that to fine tune, and it tells us the hyperparameters. Like, what is that?
No, fine tune the gradient descent of the model, right? So basically what it means is that you'll run gradient descent on this, right? So just this first half here, and then you freeze like the first half of the model, right? And so you're only updating weights in the second half of the model. Does that make sense?
Yeah.
And so that's called validation. And so you use the 30% of the data set, so the second 30% almost, right, to do that validation.
Is that still?
It's just gradient descent again, but you've frozen half the model.
And like, how does that relate to hyperparameters?
How does it relate to hyperparameters? Actually it should be fine-tuned parameters.
Oh, okay.
Is that what you mean? Yeah,
Yeah.
that's actually an error there. So it should be fine-tuned parameters, yeah. Other questions?
I mean, do we fine tune are there hyperparameters that we fine tune?
You can fine-tune, yeah, actually it's in the next section, but you can do things like grid search, which is searching through hyperparameters. I'll also need to explain what hyperparameters are, but it's a little bit more apparent later on, yeah.
For the next slide, so each one of those like 5 different folds, they
Yeah.
would have slightly different weights.
Say that again, sorry. So each fold has slightly different weights.
Is that true? Like each model would be like very slightly different trained on.
You mean like this, if you run this?
Yeah.
You actually do it sequentially. So you do this, and then this, and then this, and then this. Does that make sense?
Okay.
Yeah.
Okay.
Yeah.
So just clarifying, is it always the first half that's frozen, the second half that's unfrozen?
No, so that, yeah, I'm saying half or whatever. It could be, it really depends on what you want, right? Sometimes it's 80% of the model, sometimes it's 50, could be anything, yeah. So people experiment with that as well, yeah.
Is it you do like 50% and then you do the other 50%, or you just do?
No, so you freeze the model. So as in the weights become frozen, so they never get updated again.
As in like you then fine tune the other half.
Yeah.
But then do you unfreeze it and then freeze the other? Or do you swap?
No, you never swap. You never swap. You just do the last half. Yeah.
With the k-fold
Yeah.
calculation, so you're training it 4 times, right?
Yes.
So then, are you just going to take, in terms of the parameters that you actually use, like the optimized weights, are you just taking the one from the fold that produces the best
No, you're running the whole lot,
Oh,
right? Yeah. So you run like as in your
So you do each fold sequentially after the other one. So the other one, so
Yeah.
you do the second fold, the second row.
It's the
You've
row,
already trained
yeah.
on the first one, so you've already got that.
yes,
Yeah. Okay.
exactly. Yeah, yeah.
Okay.
Other questions? Okay, cool. Now let me just take a look at this again. So validation used to fine-tune hyperparameters. Yeah, okay. So actually, yeah, just for simplicity, this one here is when you freeze the model. And so, I mean, this doesn't happen much anymore because we've sort of moved a little bit past it, right? But that being said, you might see it in some papers, and that's what they've done, which is they've frozen half the model, for example, or 80% of the model. And do you recall why we do that? So do you remember what the earlier and the later layers actually did in neural networks?
Starts like looking at
The edges, right? Yeah. Yeah, the low level features, right? And then the later layers are looking at the high level features, right? And so what you're actually trying to do is improve how it's looking at the high level features. Okay, so that's sort of the purpose of why you freeze the initial half, right? And then you let it continue to learn the high level features. Yeah, does that make sense? So that's conceptually why you do that. Yeah. And so sort of related, and I can't recall if I have a slide here, but say you have a neural network that's trained on spotting pneumonia and chest x-rays, right? And you've trained it already, right? And you want to then modify, and you want to take the same neural network that you've already trained and then apply it to seeing heart failure and chest x-rays. What would you do conceptually? So you want to use the same model you previously had. How would you do so? Fine-tune, yeah. You again, so you'd basically freeze the model, right? Because the earlier layers, it's detecting edges on the chest x-ray, right? It's not really important, right? Heart failure versus pneumonia, it's rather that it's the high-level features it's needing to detect, right? And so you'd take that model, you'd freeze like the first 80%, and then you get it to fine-tune on the heart failure data set. Does that make sense? So that's a concept called transfer learning, right? Which is you take a neural network trained for something else previously. It does really well with the small low-level features and the chest x-ray and the mid-level features, right? And then for the high-level features, you need to modify it, right? So that it can learn from the heart failure data set and be really good at that instead. Does that make sense? Yeah.
So is the key point of that validation set, freezing the data is mainly for portability of neural networks?
Not quite for portability. It's actually like if it's just one data set you're validating on, right, and training on and so on, then it's rather you're just trying to find the value very carefully, right? Like conceptually.
Train on the whole 80%.
Sorry?
Instead of rather than letting like all layers of nodes train on the full 80%.
So could you repeat the question?
Like,
yeah.
because with validation you're like freezing some layers, right? You're only keeping like the
Yes.
the later ones.
Yeah, the later ones free. Yeah.
Why wouldn't you just let all of the layers train on the whole 30%?
Yeah, it's because again, it's that you're finding like exactly you've sort of roughly found where the valley is, right? And so you're finding even like finer parts of the valley, if that makes sense, right? Yeah.
But as in like running full 80% wouldn't find.
Not necessarily, right? Because it's that's why I guess it's called fine tuning, and that because you're taking I guess like almost bigger steps, right? Like initially, right? And then you're sort of in the valley already. You need to find like even more finely where the valley is, right? If you sort of zoom in, right? Yeah. And then it's also used, so that's different. It's the same method, but it's different conceptually to why you'd use it for transfer learning, which is you use it for a different task, right? A similar but slightly different task, right? You need to again freeze the model and then change the last few layers and update that, right? Because the model initially would be really good at detecting pneumonia, right? But that's a high level feature. So you need to modify that and update those weights in particular in order to do it, to use it for heart failure. Does that make sense? Yeah. So transfer learning is it's a cool concept, right? And actually one of the reasons why we have things like ChatGPT is because we've learned how to harness transfer learning to the extreme, right? Because initially the large language model will learn so much knowledge about the world, right? And then we need to use it to be able to answer questions effectively, right? So it's you see how it's like just transfer learning, but taken to the extreme, right? Okay, other overfitting methods. So again, a lot of these, we sort of reason a little bit backwards, like someone sort of tried it and then it worked. And so we sort of tried to figure out why. So in regularization, what you do is you add a term to the loss function itself. Okay? So if you recall, this is our mean squared error here, right? And then we basically just anchor it with a new term. Okay? And what exactly is that term? So that depends on the type of regularization we want. But the intuition behind this is that we anchor our weights so they can't change massively. Okay? So the weights are sort of almost like held in place. Conceptually, it's a little bit like reducing the steps that we can take, right? Because the weights, you know what I mean? Like we can't move as much, right? But yeah, for some reason it adds stability, right? To our gradient descent.
Is that something you do throughout the training, or would you?
You would do it constantly. No, you do it. Oh, I don't know. I don't know if anyone's ever experimented with certain times where you do it.
Like
Yeah.
doing it for validation instead of doing it for.
Yeah, that's a great question. I believe it's primarily for training, but they do it for validation as well. Yeah. So what do you usually add, right? So it's usually a sum of all the weights, right? So again, someone I think tried that. It worked really well. And there are multiple types that you might see around. So L1 or lasso regularization is just an absolute sum of all the weights. L2 or ridge regularization is a square of all the weights, right? And then L1, L2, which is called elastic net, is a sum of both L1 and L2. Okay, so an absolute plus the square. Now, do you have any sort of intuition about which one is heavier or lighter, or like which one provides a bigger anchor? Yeah.
I see the elastic one, adding more stuff.
Yes, exactly. So that's going to be the heaviest anchor, right? L2 is sort of in the middle, right? Because it's just the square. And then L1 is the lightest, right? Because you're adding just the absolute sum of all the weights, right? And so what we generally use is L2 because it's sort of middle of the road, right? It doesn't anchor it too much and it doesn't anchor it too little, and it seems to work well. Okay, so that's regularization. Another idea that someone tried and it worked really well is called dropout. So in dropout, for each forward pass, you randomly turn off 50 to 90% of all neurons. Okay, so just let that sink in. During the forward pass, you randomly switch off a big majority of the neural network. Okay, you literally just zero it out. Very unusual. So all neurons, like during testing, all neurons are back on, right? And essentially what it does is it ensures that there are no connections that are too strong. Okay? And all neurons are involved in answering, right? Because if you turn off, for example, 90% of neurons every time you're doing a forward pass, right? The neurons eventually learn that they need to spread the knowledge, right? Because if there's like 1 or 2 neurons or 10 neurons that are really important, they're answering every single time, during dropout, they're going to do really poorly, right? Because those set of neurons might be switched off. And so it spreads the load, it spreads the knowledge, and so the weights end up almost like being, you know, like the neurons are all involved in the answer, right? And so it's very robust, the neural network. Okay? Any questions? Yeah.
A few questions. So like it reminds me of, so like you want to compress, so dropout makes a lot of sense because you're spreading the information throughout the network. You're also, by turning off some, you're making, like, you're sort of almost compressing the information into a smaller density of neurons.
Yes.
So you're trying to extract like the most feature selective features, like the most selective parts of the information. You're just like making it the most condensed learning for that input. And similar to L1, in L1 you only add like absolute value addition. So like this would end up with your parameters like could tend to 0, right? Because if you have your sum of your parameters as part of your loss function, you're minimizing loss, then the unnecessary ones would tend to 0. So it's sort of almost similar to like, I'm trying to draw a link between like the intuition of dropout and like almost L1, because then both of them are having very dense learning. It's sort of like you're capturing the exact features that are necessary from the input data. Does that even?
I'm not sure it makes sense yet to me. Yeah, could you re-explain it? Yeah.
So like, I mean, I was talking to Claude as well. So
Yeah.
like, for L1 and L2, another advantage it said was, in L1 it would promote sparsity because it would push some weights to exactly 0, which makes sense. Because
Okay.
in
Yeah.
squared it wouldn't push it to 0. This would
Yes.
push it to 0. So it's good for feature selection.
Okay.
Is what it said. And
Although we don't use L1 much because it can cause vanishing gradients, which is probably what you're saying.
But like,
right?
I wonder if that's
Yeah.
actually like can be useful sometimes, because I mean not the vanishing gradient part, but the
As in, you're getting rid of neurons that are useless.
yeah, exactly, yeah.
Elastic band also does that.
Because I guess it does both, right?
Yeah, it does.
Because it does both.
That's
Yeah.
why we use it more.
Oh, okay.
Well, we use Ridge the most. Ridge is most widely used.
Oh, yeah. In like regression tasks. It's
Yeah.
pretty fast doing.
But you don't really want vanishing gradients because then the neuron's just useless, right? It doesn't do anything anymore.
Like, doesn't that mean it's better learning? No.
No, maybe from an evolution, like, you know what I mean, like if you're thinking from an evolutionary standpoint, it's like you're getting rid of those neurons, but then you have to be constantly injecting new neurons so that it can learn something, right? And maybe that's an idea that hasn't really been explored yet. But if the neuron's just disappearing, it's dead, and you can never use, like, you lose expressiveness because there's no more variable to use, right?
Yeah. I'm also thinking of how it links to like you know the bow tie, like autoencoder thingy where you're
Yeah.
getting a lot of, because that's commonly seen in biology where you have like big inputs to like one specific, very, very dense information that
Yeah, I know,
that
yeah.
expresses itself again. So
Yeah.
like, I wonder like maybe it's actually not that bad sometimes. I don't know.
Well, I don't know. I mean, like, dropout, it's you're forcing it through like a narrow channel. Like all
Yeah,
knowledge
it's-
must flow through a narrow channel,
Yeah.
but you're doing it randomly, right?
Yeah.
And then so all channels, like all neurons are involved eventually in the knowledge, right? Because 10% are only involved, right?
Yeah, makes sense.
Yeah. So you can see how like these conceptual, I mean, it's just humans, right? Like someone tried this, it worked, and now we're trying to explain back why it works, which is a bit funny, right? So I don't even know if the conceptual explanation is the reason why this works, right? It's what we think it is, right?
Why do you need a neural network to be robust? Like, why can't one neuron just do most of it? Why is that effective? Because you're running it past everything anyways. Like when you're putting in input.
Yeah, that's a great question. Why do we want it to be robust? Sorry? Yeah.
I don't see the problem with one neuron doing a lot of work, if that makes sense.
I'm just trying to think, like so there's an architecture now, we'll cover it in a few weeks, called mixture of experts, right? So apparently there's a new kid on the block for transformers, right? There's a whole company that's bet its whole financial strategy on mixture of experts, right? Like several $1 billion. And how it works is it's like instead of a giant transformer like you have with ChatGPT, you have 8 smaller transformers. And then there's another agent that decides which expert to route it to. Does that make sense? So they're called 8 experts. So you can route it to whichever expert. But then they did studies on it and they realized that one of the experts is absolutely fundamental. Like if that expert disappears, right? Like the whole system just falls apart, right? Why is that bad? Like that seems like a bad thing to me, right? So you see how the system's less robust, right?
Because like if you're like randomly dropping out like half the neurons, doesn't that just make it less able to model complex stuff? Because like you're effectively making it half as wide.
Or are you forcing more neurons to be effective? I don't know. That's another thought, right?
Yeah, sure.
Yeah. And it does better. Dropout does really help with overfitting. Like it's one of those things that if you don't have, you probably have overfit. So everyone has dropout now.
Like why don't you just reduce the width instead of doing dropout? If that makes sense.
Because would you prefer like 10 neurons that are really effective or 100 neurons that are helping out, or each little helping out a little bit, right? You'd probably get a more expressiveness with the 100 neurons. Yeah. Yeah.
Because I would think like it's computationally more cheap to just cut off half the neurons.
Yeah, but you lose expressiveness, right?
Yeah.
You do lose expressiveness, yeah. Because you only have 10 variables you can modify.
Sure.
Yeah. Other questions? This is a great discussion. And this is the sort of stuff you need to be thinking about because like it's easy to teach a dropout, easy to tell you to use it, but you need to be thinking about like what it actually means, right? And because anything that is new that's going to come up, you have to be able to understand it conceptually, right? Like why does this work in particular, right? It almost doesn't matter. You mean if the main part of this is like just use dropout, right? But like why does dropout work? Yeah.
Like, when you like when you do like the weights and devices, you actually get like a neuron as your output, right? After
Yeah.
activation time. Is it just literally like after you do that matrix vector multiplication, you just set it to 0?
Say that again, sir.
Like you know how you're dropping out neurons, right?
Yes.
But each neuron comes from a matrix vector product,
Yes.
right? So like, how do you actually get it to be 0? Do you just use like hard code, like this is 0, or do you make the weight matrix to use like zeros?
I actually don't know how they implement it.
That's
Yeah.
what I was thinking.
It's a great question. I don't know how they implement it exactly, right? Because from our perspective, in the code here, you can see here, it's just like, I literally just put in func dropout and then it drops out for me. I've got no idea how they implement it, right?
Yeah.
Yeah.
I was always wondering when I saw it.
Yeah. Well, probably whatever's most efficient. Yeah. Anyway, okay, so that's dropout. All right, batch normalization. So for each forward pass, we normalize each layer's data. Intuitively, what this means is we keep weights in a healthy range and it adds some randomness. And so in training, we normalize per layer. During the test, we normalize for the entire data set. Okay, again, why does that work? Great question, I'm not sure. And it's just something that everyone does. This is how you do it. Okay, so you can just create a batch norm layer there. So you just sort of add bn1 or bn2 to what you've already got there. Okay. Okay, gradient clipping. So I think this one makes a bit more sense. If the L2 norm exceeds the max value, all weights are scaled down. Okay, so if it's like you're seeing that the weights are exploding, you just scale it down. Okay, I think that's a very logical one, so it prevents exploding gradients. So again, yeah, that one seems pretty straightforward. All right, residual or skip connections. So this one here is an interesting idea that came out of the vision field, but is now used in transformers as well. So they basically just realized, and I'm sure someone just literally tried this, if you put a connection between early layers to later layers, right, like a direct connection. So you know how like generally if you have a neural network, like what happens here has to go through this, has to go through this, has to go through this before it reaches this. So it's really processed, right? But you actually just provide a direct connection between this and this and this and this. And then you do it for every other layer, right? So those are called skip connections because you're skipping layers, okay? And it allows future layers to access earlier information directly, okay? So it gets a cleaner signal. So it gets both the processed signal and the clean signal as well. And it's super weird, but like this is actually what the lost landscape looks like, right? Without residuals, and then with residuals, this is what it looks like. Why? I don't know, right? Like it's a great question. But it works. Okay? And as you can see, as you know, when you're imagining your loss function, like this is a horrid loss. Like this is horrible to work in, right? This is absolutely horrible. Your loss is going to go everywhere, right? But then this is very, very nice, right? Like this, your loss is always just going to consistently go down. Okay? So residual connections. Okay, now other ideas. Model ensembles. So this is another idea that's been re-finding popularity recently. It's quite funny, the AI field, it just, something new, exciting happens, and then we discover these new, these really old ideas that we've had since like 2010, and then we just reapply it, right? So model ensembles, that you basically train several independent models, and then you average the weights at test time. And for some reason, it does quite well, right? And so someone's like, hey, can I train a bunch of transformers and then just average the whole lot? Okay, and it also does quite well. Okay, so don't know why. Right, transfer learning. So this is what we were talking about before. So we learn knowledge in one domain and then we transfer to another domain. And so for example, it could be you pre-train at one task and then you fine tune for another task. Okay, and I like this picture because it's sort of like transferring the brain, right? And so for example, you could pre-train it like how to diagnose pneumonia and then fine tune it at diagnosing heart failure. Okay? In transformers, what we're pre-training is the whole knowledge of the world, and then we're fine-tuning it to be able to answer our questions. Okay, so that's an example of transfer learning. Obviously, this is much more powerful than random init because you're already at somewhere down the valley, right, before you start fine-tuning again. Okay, so it's always a good start. It's traditionally done via frozen layers, right? So like I was saying before, but with transformers, we actually don't do that. We just use the entire model, and then we fine tune some parts of the model, which we'll talk about.
How do you
Yeah.
How do you know whether something's transferable to something else or not? Like I'm thinking in terms of like
Yeah, where's the threshold? It's, yeah.
in terms of like the X-rays, like maybe you can do all the different types of test X-rays.
Yeah.
But then could do it like an abdominal X-ray, like
Yeah, I have no idea.
Okay.
The answer's on a spectrum, right? Because it's like if you can, I expected maybe the answer's like from the probability distributions. You remember the KL divergence, right? Like there's two probability distributions, and it's like how much overlap is there between the probability distributions of what you're seeing, right? My guess is the answer lies in that, but we don't have a hard threshold, right? Really, like you can do this, you can't. It's the unfortunate answer is just you have to give it a try, and then it either works horribly or it works well. Yeah. All right. Any other questions? Okay, let's discuss loss curves. So loss curves, they measure loss or error over time. Usually it's very, and you've probably seen the numbers now, it's a steep improvement at the beginning and then it sort of peters out a little bit, right? Unfortunately, loss curves in real life, as you can imagine, actually look like this, okay? So this is a dream that we all have, right? Like, love to see this. Unfortunately, it looks like this, right? So it's really hard sometimes to actually figure out when you're supposed to stop, right? And this obviously happens, you know, the more stochastic you go in terms of like it's one example or whatever, right? And if you're measuring loss every time, absolute nightmare, right? Now, in terms of debugging loss curves, there are a couple of things. So if you see a plateau like that, that usually indicates that you may have had a bad weight initialization, right? And so you could restart, okay? You could just restart and then hope that you land somewhere else in the landscape. This here indicates that the loss is steadily decreasing, but your learning rate is probably too slow. Okay, so if it's sort of like still decreasing but sort of petering out a little bit, try increasing the learning rate and see if you can get the loss to decrease faster. This is great. I mean, if you see this, very happy, right? Healthy loss curve plateau. And at this point here, you could try smaller steps, right? Because you've sort of reached a valley of some sort. And the question is, can you find even the smaller valley within the valley, right? And the only way to do that is to try considering smaller steps, okay? Because it could be that you're sort of just going around the rim of a valley, okay? If you further decay learning rate too early. Okay, if you decay the learning rate too early, right? Then it could also be that you're not taking big enough steps to get into the valley, okay? So again, when you're looking at loss curves, it all comes back to that landscape imagination, right? Like think about where you are in the landscape and how you're sort of going down that hill, right? And usually when I think about that, it sort of becomes quite clear what the answer needs to be in terms of what you need to test next, okay? Any questions about these? Okay. All right, so early stopping. So as we mentioned before, this is when you stop training, right? When the test and the train curves start to diverge, right? Because basically what you're doing is you're overfitting, okay? So you're overfitting to the train data. It's learning really well for the train data, but then it's generalizing really poorly to the test data, okay? And so the sort of variables that you need to be aware of is patience and min delta, right? So patience is the number of epochs to wait for improvement before stopping, okay? Because remember, it's really noisy, right? So if you, for example, wait longer, then it could be, you know, diverging a lot more. And if you wait very short, then it could just be a small blip, okay? That's happening. So the patience sort of, it's like how long you're waiting. So hence the word patience. Min delta is the minimum change in validation loss to count as an improvement, okay? So this is related to patience, which is how long you need to wait for an improvement, and you actually define the improvement via min delta. Okay, so I'll get you to actually play with this in the example that we have. And so those are the sort of two parameters to decide when you need to stop, okay? Now what we're gonna be using is something called TensorBoard, right, which is just a way to actually track it. But there's lots of other programs as well, and so in the wild, right now, is what's really popular is something called 1B, or weights and biases. And so people really like this one because it's really colorful and it's really quite nice, right? And so weights and biases is another sort of thing you might see for loss curves. Okay, hyperparameter optimization. So we've been talking about parameters, which refer to the weights of the model. Okay, so when we always say parameter, it always refers to the weights of the model. Hyper means something above that, right? So it's the parameters which are, for example, the number of layers in your model, or the learning rate, or the things that you've actually been playing around with as a human, right? So those are all called hyperparameters. And so as AI engineers, you'd imagine that someone asked, can we use AI to pick the best hyperparameters? Okay, so we're not sort of guessing and picking random numbers or having sort of religions about which number we should have, right? So trial and error is obviously very cost and time consuming, right? You don't want to be sort of sitting there and trying like every possible number for all these hyperparameters, right? And obviously with the curse of dimensionality, I mean, if you try like 3 numbers, even for each of these, right? That's like 3 to the power of 9, right? Which is how many runs you have to do to systematically figure out what's best, okay? And so some of the examples or some of the techniques that we've come up to deal with this is called grid or random search, which is when we systematically or randomly search the hyperparameter space for imported parameters, okay? And so as a human, again, you have to define this. It's like, I want to try a small learning rate here of 0.001, and I want to try a large learning rate of 1. Okay, so you still need to define that, but this program will automatically search sort of in a grid pattern for you, right? So it tests like all the different values, or it might also do it randomly. So it might just choose a random value between 0.001 and 1, and then just see how well that works, okay? Now grid and random search, as you can imagine, is not that efficient either. There are more advanced techniques, and this is sort of almost beyond the scope a little bit, because this is where you're getting to industry, where every run might cost like, 100K or 200K or something, so you don't want to be wasting a huge amount of money trying to do the runs, right? But the technique that they use in industry is called Bayesian optimization, and it is math that I don't fully understand, right? But it builds a surrogate model to predict what hyperparameters might actually work for your specific model, right? And then it actually provides recommendations on what the hyperparameter should be, okay? This is starting to get quite complex stuff, right? Like this is not stuff that you need to know, but you do need to know that it exists, right? And this is how sort of industry actually finds the perfect hyperparameters, okay? Any questions? Okay, cool. So, to sort of tie everything up, right? This is what a state-of-the-art neural network looks like as of 2014. It's been roughly the same since 2019, right? So not much has actually changed over the last 5 years, right? So we've already talked through some of this stuff here, so it should all look familiar. For overfitting, generally use k-fold cross-validation for neural networks. They are not really used, like this strategy is not really used for transformers. L2 regularization, dropout, batch and layer normalization, right? So again, batch is not widely used for transformers, but layer can be. Gradient clipping and early stopping. And then for tracking, the gold standard is either TensorBoard from PyTorch or WANDB, or weights and biases, which is very popular right now. And then hyperparameters is usually Bayesian optimization with Ray2, which is a sort of company thing, or grid and random search for most other people. Okay, so let's talk a little bit more about data and compute. So how much data, right? And so this is the neural network version, right? And so it depends on the task, okay? So if you have less than 50 data samples, it's probably a no-go for training an advanced neural network, right? You can consider things like regression, some of the simpler techniques that we talked about. 50 to 500 samples, maybe, and then sort of above 500 is the sweet spot for when you can be quite comfortable building a simple neural network, okay? So that's sort of just, if you get pulled into a research project or whatever, that's sort of the number of samples you should be asking for, okay? And there's lots of I see medical papers or medical projects here all the time where it's like, they had 40 samples or 40 patients or 60 patients and they're trying to build a neural network. Like it's maybe doable, but it's not gonna do very well at all, right? And so 500 is when I'm like, all right, maybe we can build something quite simple, right? And then as you scale up the numbers, then you can build sort of more advanced neural networks. Does that make sense? Okay. All right, how much compute? So how do we actually even think about compute? So I've been throwing that term around a little bit. So compute just basically means that we're doing a mathematical operation in a CPU or GPU, so a processing unit, right? And the way that we measure that is in something called a flop, right, or flops. And that stands for floating point operation per second, okay? Now, have you guys heard of floats before? Do you know what a float is? It's a decimal point number, okay? And so because, as you've seen from this, like when we're calculating dot product and all that stuff, right, like doing gradient descent, it's all just multiplying numbers together, right? And so we need to calculate how many numbers we can multiply together in a single second. Okay, so that's how we actually measure the performance of GPUs and CPUs. GPUs, which were initially created for games, right, were found to be really good at multiplying numbers together. And part of the reason is that, again, when you're creating a game environment, right, you need to multiply a lot of numbers together. So it just happened to be sort of serendipity. And so what we have right now, and what is state of the art, is called the NVIDIA H100. Although I think in January next year, this is going to be old, right? It costs around 25K, and it can do 2 petaflops, which is 2 times 10 to the power 15 operations per second. Okay, so that's how fast these graphical units are. Now Google's TPU, which is something that you can actually rent on Colab, right, for about 1.2K per month. This is 393 teraflops, so 393 times 10 to the power of 12, which is, I guess, like slightly less than that, so it's like 1/6 of that or so. And then the human brain operates at around 15 petaflops, okay? So it's sort of very interesting to see where the current technology is. So current technology is, what's that, like 1/10 or 1/8 or something of the human brain, okay? But that being said, the human brain itself is an analog system, okay? And so these are digital systems, and analog systems have a bit of an advantage in that with analog systems, you basically have memory and compute in the same unit. Okay, so that's, we use the neuron, right? And so because of things like long-term potentiation, neurons can have memory when they compute. Does that make sense? When they're trying to do a calculation, they have memory because of long-term potentiation, which is just, the receptors, how many receptors there are at the interchange, right? With computers, unfortunately, they have a system where memory and compute are completely different things, okay? And that's called a von Neumann architecture. So it was created by a guy called John von Neumann, right? And he happened to create a system whereby when you compute and you have memory, it's a different system. And so there is a communication talk between the two, right? And so it's inherently a less efficient system because there's time required to be able to talk between the compute and the memory units, okay? So biological systems, even though the human brain is estimated to have this, I don't know what the analog benefit is. It's probably massive, right? And so it's unclear if these are going to be sort of equivalent to the human brain just yet, even though these numbers look quite the same. Now, a single backpropagation for a neural network is around 1 to 10 million flops. Okay, so you can sort of actually back calculate how long it sort of takes, right, to train these systems. Convolutional neural networks, which are the main sort of image recognition systems we had a few years ago, is around 100 million to 1 billion flops. And then transformers, so modern transformers are around 1 billion to 1 trillion flops per backpropagation. So don't forget that we run backpropagation like millions of times, right? Or billions of times. So as you can see, yeah, so that's why there's been a bit of a gold rush to buy these things, right? Like people were dining with like NVIDIA CEO just to get that, right? And so yeah, so that's sort of how you think about compute. Any questions about this in particular? Because compute starts to get a bit important as we're dealing with large language models, right? And it's something that you actually need to factor into calculations. Okay, so you sort of need to understand how flops work and how much flops we have and how much, a single back propagation actually does, because it's sort of simple math to work back how long it takes, right? And you can even use these calculations to calculate how long it takes to actually train your thing, right? Because even adding an extra 0 might be the difference between 2 years to train this and 20 years to train this, right? So it's a huge difference, yeah.
This kind of sounds like a weird question. But
Yeah.
With CNNs and transformers, the numbers of flops are different, right? That's a rate though.
Sorry?
Because it's the floating point operations per second.
Yeah, floating point operations per second.
So like my question.
Yeah, it is a rate. You're right.
Right,
Yeah,
rather
so
than
it's actually the number of, yeah, so it actually should be floating point operations.
Yeah. Okay,
Yes, yeah,
because
yeah,
that's why I was like,
yeah.
why would that
That's my bad, yeah.
Okay.
Yeah. Other questions? Okay, cool. All right, so let's work on this exercise here. So the URL for this is slightly different. It's just a 1 at the end there because I couldn't get the number 2. So work through those exercises there. Because it is a Friday afternoon, I've made it a little bit easier. It's more of a reading exercise just to see how we've implemented some of the anti-overfitting stuff. Okay, cool. All right, so I hope you've got some time to play around with some of the overfitting stuff. So you're getting sort of to the point where you understand some of the key aspects of neural networks, right? And like I was saying with this table here, real AI engineers these days don't really code much anymore. It's rather you're just supervising code, right? You're just supervising, honestly, like ChatGPT or Claude to write it, right? And then you're modifying what you think needs to be modified, right? But, again, the code, you need to sort of look at it, you need to understand it, right? You need to understand some of the key hyperparameters that you want to modify if something doesn't work out. Unfortunately, ChatGPT can't optimize your neural network for you just yet, right? And so you need to be able to do it yourself. All right, so let's talk about performance, right? And so performance comes back to this matrix that hopefully you're familiar with from med school, right? Like sensitivity, specificity, so on and so forth, right? And so this is sort of, I didn't learn this in med school, but software engineers call this the confusion matrix, right? And I sort of chuckled at that because I'm like, yeah, this is really confusing. But sensitivity and specificity, we actually have slightly different names in software engineering. They happen to be called precision and recall, right? So if you happen to see precision and recall, they just refer to sensitivity and specificity, okay? And then accuracy is another metric that actually combines all 4 of these, okay? So it's like true positives and true negatives divided by all 4 cells, okay? So again, just terms that you'll see. When I first saw precision and recall, I sort of like, what was that? And then I was like, oh, it's just sensitivity and specificity. And that's something that I'm familiar with. Okay, so let's talk about how we actually measure accuracy, right? And so this is really critical when it comes to actually building stuff for medicine, right? Because we sort of need to tailor it to what we're building, right? And so accuracy itself is not a great metric, so please don't use accuracy, right? You might actually see it used in some papers, some really old papers these days. And part of the reason is that it's not great for class imbalances. So if, for example, there's a disease where, it's a really rare disease and then it's, common to not have it at all, then accuracy sort of performs really poorly, right? Another thing you might see, and again, this is quite old now, is an F1 score. And it's just, I don't even know why it's called F1. I was just thinking like Formula 1, right? But yeah, it's not great because it doesn't account for true negatives, right? And part of the reason is it accounts for only precision and recall. And if you take a look at this table here again, precision is these 2, recall is these 2, and so it sort of ignores the true negatives, okay? And so we always want a metric that accounts for all 4. Now, the sort of metric that is quite widely used at least a few years ago, I don't know if it's still used as widely now, is the receiver operator curve, or this graph here, right? Which maps true positive on one end and then false positive on the other. And it's always an absolute nightmare if you've never seen this to actually learn how to interpret it, right? But this line here, so if you ever see a line like this basically is a random guess. Okay, so that's how well a random guess does. Okay, and then this is better than a random guess, this is better, and then this is what a perfect classifier looks like. Okay, and then how we sort of record how well it does is the area under the curve. Okay, so a perfect classifier, the area under the curve is a square here, which is 1 by 1, so a perfect rock would be 1. Okay, does that make sense? So that's a perfect classifier. A random classifier is 0.5. Okay, so it's kind of funny, but sometimes journals get really excited when you report a rock of like 70 or 60%. But recall that 50% means that you're randomly guessing. Okay, so 60% is not so impressive, right? Because you're only slightly better than random. Does that make sense? Okay. All right, cool. So that's the rock curve. Now the rock curve, unfortunately, does have some limitations, which is it's only one curve per binary classification problem. Okay, so if you have like a multi-class thing, so say you have like n categories, then you need n ROC curves. Okay? So obviously that leads to problems. If it's like you're trying to predict like 20 diseases, you need 20 ROC curves. Okay, so it's not very interpretable to everyone else. All right, now can anyone tell me what an area under the curve of 0 means? Yeah, it's perfectly wrong. Exactly, okay? It's perfectly wrong. So I don't know, if you ever, in that scenario, just flip the labels because your model's so bad that it's so good now, right? Because you can just reverse all your outputs and you're going to be perfectly correct, okay? Does that make sense? So if you ever see an AUC less than 0.5, it's worse than random, okay? But bizarrely, because you can just simply change your output labels, right? You can flip it so that the model does surprisingly well, okay? Very unusual. All right, so how you interpret or read a ROC curve is that points that lie on the same ROC curve have the same performance. Okay, it's sort of an unusual thing, but if, say, for example, I had a point here, a point here, a point here, it actually indicates the same performance. Okay? So, how I talk about this is sort of like imagining a doctor, right? And they've actually done studies on this, right? And I can sort of share with you some of the interesting insights. But say you are a conservative doctor, right? This means that you would have a low false positive rate, so you're not telling people the wrong thing, right? But you also have a low true positive rate because you're very conservative about giving a diagnosis. Does that make sense? So that's where a conservative doctor would lie. A less conservative doctor, which tells everyone, you know, they might have this, might have that, right? They're going to have a really high true positive rate, so they're accurate when they're right, like when the patient actually has the disease. But they will also likely have a high false positive rate. Does that make sense? So this is related, if you're sort of thinking about it, to that thresholding that we were talking about, right? If you set a really high bar, right, then you're a conservative doctor. And so you sort of get it right, or sorry, get it wrong a lot less, but you also get it right a lot less as well. Does that make sense? And if you're less conservative, then you're telling everyone they have the disease. You're going to be right a lot of the time when they actually do have the disease, and then also wrong when they don't have the disease. Does that make sense? So it's related to that thresholding. Now, they've actually done studies on this, and human doctors typically stay on the same ROC. Okay? So it just sort of depends on how you're feeling that day, right? Whether you're sort of feeling conservative or not conservative, but you sort of roughly stay on the same ROC. So it's very funny to see. That being said, the ROC, or this area under the curve, can improve with training. Okay, so that's great news for like colleges and med schools and stuff, because as you sort of get more training, you get more accurate as a doctor, right? That being said, you never get to perfect though, right? You're never a perfect doctor. Okay, so this again is another sort of representation of it, right? And this was from a famous study in dermatology, which used AI to compare against dermatologists, right? Just to see how the AI was going. So the AI line is in black, so that's the ROC curve of the AI, right? And these individual points here were different doctors, right? And so this dermatologist here was very conservative, right? But again, roughly the same accuracy. These were sort of middle of the road. And then this person here was not conservative at all, right? Like they just said yes to everything, right? So very accurate, right? But then also very wrong when the patient didn't have the disease, okay? And then there's just this like freak person here is weirdly accurate, right? So you see how they're on a different ROC curve, right? So that dermatologist, that would be my dermatologist, right? If I go to them, okay? Any questions about the ROC curves or how to actually interpret them? All right, cool. Okay, so how do you actually select which points? And there's lots of different philosophies to this. This is not like gold standard or anything, but this is one way that's been suggested. And you basically select an operating point that accounts for both sensitivity and specificity. And it's called Newton's J index. And then you just basically calculate this J by having sensitivity plus specificity and then -1. And then that helps you calculate at which point on the ROC curve you should be operating, right? Because the ROC curve is always not a smooth function, right? It sometimes can be quite jagged. And so you're trying to find the best one, right? Like the one that's closest to the top left corner. Does that make sense? Okay, so let's talk now about historical neural networks. So we're actually sort of done for neural networks in terms of what you're doing, but a little bit of history now just so that you can see, you know, you might see terms that you're like, what on earth is that, right? There's been sort of a long history of neural networks, so it's worth sort of spending some time on it. So perceptron was created in 1958, okay, by a guy called Rosenblatt. It was a single layer neural network. It was primarily just for binary classification, right? And it was just someone honestly looking at regression and being like, hey, like we could represent this as a neural network, right? Or as a perceptron, as they called it. Fast forward about 20 years later, and then a gentleman named Hopfield, who just won the Nobel Prize this year in physics, created something called the Hopfield network, right? And this was a time when, you know, the field was sort of still in a frenzy and sort of very excited about the stuff that could come. And this was fully connected network, so that is each neuron is connected to every other neuron. So you see how it's not really like a layer structure like we have, right? Each neuron is just connected to every other neuron. And so those are called fully connected networks, and they memorize patterns, right? So they were inspired by some neuroplasticity stuff, so Hebbian learning. And so basically when you provide a prompt, it just finds the closest pattern that it's previously learned. Okay, so that's what a Hopfield network is. We don't really use Hopfield networks, but maybe they will have a comeback at some point. Now in 1985, someone came up with the Boltzmann machine, and that's Jeff Hinton actually, so he was also the father of the neural network. These were similar to neural networks, but instead of sort of telling you the closest pattern, so pattern matching, it would generate new patterns. Okay, so it was like sort of our first generative AI. You know, we use that term now, but this was the first generative neural network, okay? They were called Boltzmann machines. In 1986, Hinton then came up with the multi-layer neural network, right? So he took a look at the perceptron and realized that you could actually stack them, okay? And that's when he invented backpropagation. Autoencoders. So in 1986, Hinton again and colleagues created a very powerful compression network, right? Whereby you basically just have this multi-layer neural network whereby you bottleneck information at some point, right? And so what that was very powerful at was that you have a lot of information here. You compress it to the key features. Okay, so because you're bottlenecking information, it becomes the key features inherent in this information. And then you use that to basically reconstruct some of the features. And so what that was really critical for was that you could actually extract out the most important features of a data set, right? And so you'd actually be looking here to see what comes out. Does that make sense? So when you have a lot of data, you want to see what the most important features are, maybe features that you even missed, right? And so this is a very powerful way to achieve that. Okay, 1997, recurrent neural networks. So these are neural networks that basically looped back on itself, okay? So we haven't talked so far about recurrence, which is when you have future layers that loop back on earlier layers. Okay, so sort of a very interesting concept. These are called recurrent neural networks because there is recurrence here, right? And the whole purpose of this, or the whole point of this, was that it provided memory, right? So it was sort of the first representation that we had of memory, right? And so these have fallen out of favor a little bit, but even when I sort of joined AI in around 2016, these were sort of a hot thing to be working on, right? Like RNNs, LSTM, which is long short-term memory neural networks, and then GRUs, which are gated recurrent units. And so that's what people used before transformers, right? It didn't perform that well, and it was sort of really unstable to use, right? Because as you can imagine, the weight's sort of cycling back on itself constantly, right? And so you'd have like vanishing gradients or exploding gradients constantly, okay? Right, 2012, 2015. So this was when people were trying to deal with images, right? So we had sort of neural networks with like data like house prices, that sort of thing. And then people were like, how can we deal with images and videos, that sort of thing? And so that led to the invention of the convolutional neural network, which basically views the image as these patches, okay? And so obviously when you look at an image, right, what's right next to like this pixel here is really important. What's like next here is really important. And so proximity really matters, right? And so the convolutional neural network introduced the concept of considering stuff next to each other, right? Like in an image, you always have to look at the pixels next to each other, right? And so you might see these words around. So LeNet, AlexNet, VGGNet, ResNet, and UNet for some reason, UNet is very, very popular in medical studies, right? Like lots of labs still use UNet to this day, right? And so UNet is a very popular thing. If you see that, it basically just means that that lab is trying to deal with images in a somewhat old way now. Okay, we have sort of more modern techniques. All right, 2014, generative adversarial network. So this was by a gentleman named Ian Goodfellow. And he had this sort of idea that was quite wild at the time, which is instead of having one system to generate stuff, you actually have two systems. So the first AI system would generate a fake image, and then the second one would try and discriminate to see if it was a fake or a real image. Okay? And then when you have sort of these two dueling AIs, they eventually train and get really good. Right? So one is really good at generating a fake image, and then one is really good at telling the difference between a fake and a real image. Okay? So everyone got really excited. The only problem is that because you have two dueling systems, it becomes really unstable, right? Because if one sort of goes off whack, the other one goes off whack as well. Okay? So the problem with these GANs was that you couldn't get stability. All right, 2016. So this led to sort of a huge rise in reinforcement learning, right? And so you might have seen stuff from actually some OpenAI stuff. Google DeepMind was a company that was huge in this space as well, right? And so how reinforcement learning works is that it's actually inspired by Pavlovian biology, whereby you have an agent in an environment, right? And that agent environment can be defined quite broadly. So for example, it could be, let's see, like a Dota team in a Dota environment, right? Or it could be a surgical robot in a surgical field, right? So agent environment can be defined very broadly. It could be a human just operating in the world as well, right? So agent environment. The agent would take an action, and then that would change the environment in some way. And then so therefore the environment would provide a reward to the agent, and then the agent needs to detect how the environment has changed in its state. Okay? And so there were sort of three important things that you had to define for reinforcement learning. The first was the model, which is the agent's representation of the world. The policy, how to choose the best action. And then the value, which is the prediction of the expected future reward. Okay? So this led to the ability to solve really complex environments that we sort of didn't expect to be able to solve, right? So for example, you know, training an AI team to play Dota is actually really complicated, right? And so you need to have something like reinforcement learning in there, right? What we're seeing it used now for is one, to actually make transformers better, right? So you can actually frame transformers as a bit of a reinforcement learning problem. And you actually see that we use some reinforcement learning in the training. And then the second right now is agents, right? So that is AI that needs to see in a really long time horizon, right? Reinforcement learning provides the structure for that. Does that make sense? Any questions? Okay, transformers, we're going to talk all about it next week, so don't worry about it. This is the sort of new architecture, and we're actually going to break this down step by step, right? So you can understand the transformer completely. But this is the sort of new architecture that has sort of hit us, right? It's GPT, it's the T stands for transformer, right? Everything that we use now is transformer based. Very, very cool. It was actually discovered in 2017. It only hit the mainstream about 2021. Okay, so it took 4 whole years before people even realized what this was, okay? All right, and then just a quick sort of overview of machine learning in general, right? So this is the sort of terminology soup that you're going to see around. So AI is just an umbrella term for intelligence from a machine. AGI, which we're actually going to spend a little bit of time talking about, is AI that can do everything that a human can do. So it's the G stands for general, right? So general intelligence. ML is a subset of AI that focuses on database statistical learning. DL, or deep learning, is a subset of ML that uses neural networks in particular. And then generative AI is a subset of ML that uses transformers. Okay, so you're trying to generate information. All right, other terms. Now you've seen hopefully what supervised learning is. So that's when you provide answers. You provide a ground truth for the model to be optimizing towards. Okay? Now part of the issue of supervised learning is that it requires a lot of human effort, right? Like for people to label what the answer is, particularly in medicine, it's basically getting like an army of dermatologists to label your dermatology images, right? So it's stuff like that. That's what supervised learning is. Unsupervised means that there's no ground truth. Semi-supervised means that you label a small amount and then you try and bootstrap your way out, right? So you could label, for example, like 5 really important examples, and then you get another machine learning to label the rest based on the 5 that you've labeled. Does that make sense? So that's semi-supervised. And then self-supervised, which is actually what we use for transformers. The model creates its own labels from data, okay? And we'll talk about what that actually means, right? Because unlocking self-supervision has been critical for us to train the entirety of the internet, for example, right? Because if you had human people labeling the whole internet, that would be absolutely nightmarish, right? And so you have to get the model to do it itself. All right, we've also talked about this. Offline learning is what you've been doing so far, which is you have a data set and you just sort of train something. Online learning means that you have a constant new stream of data, right? So it could be like users who are clicking on your website or whatever it is, right? Or it could be new scans coming in, right? In the radiology department, right? So that's online learning. And then another thing that's quite popular in healthcare is something called federated learning, which is the model is actually trained across multiple devices, okay? And so it actually sees the sample, say for example on your phone, right? It sees the sample on the phone, right? It runs gradient descent on the phone, so it updates the weights, and then it comes back to central, right? So it comes back to the central server, and then it goes to another phone and does that, right? And so you see how the training example never leaves the phone, right? Because the weights are brought to the phone. Okay, so that's called federated learning. It's a very popular idea in healthcare because that way, no sort of private or patient data ever leaves the hospital. Okay, so a very popular idea. All right, now other types of machine learning. So we talk about neural networks, but that being said, there are lots of other types of machine learning as well. These have not become as popular because they haven't found huge amounts of success, right? But that being said, you still might see them around in medical studies. So just sort of keep an eye out for them. So support vector machines, it is so that bracket S there means it's supervised, right? If you see bracket U, it means unsupervised. Support vector machines is a basic classification method which separates the positive, so for example, class A here and class B, using a hyperplane. So it actually just draws a graph, like a line, in between two categories, and then it provides like, you know, like that is group A here, and anything above that line is group A, and anything below that is group B. So it's sort of a classification thing that you might see around. Quite old now, I think like 2013 to 2016 was when these were popular, but hopefully you don't see them around, right? If you see them around, sort of big questions. All right, another one is decision trees or random forests. So this basically splits the data into subsets based on feature values, right? So it's sort of like almost like a decision tree that you just basically, you know, making decisions at. It's like, you know, are the house prices above 50K? Is it below 50K? Is it, you know, the latitude is this, the longitude is that. So it's just like forcing sort of features to be split into decisions, right? And so random forest is an extension of that idea, and it's basically multiple decision trees, right? And you can combine their outputs either by a majority vote or an average, okay? So again, an old idea that you might see floating around. K nearest neighbor. So this is when you basically create an algorithm, right, to see what sort of clusters might be around a certain data point, right? So actually go through this GIF here. So say I have this sort of set of green here, this set of red here, and I have a black point. So this black point, we don't know if it's red or green, right? And so it actually just searches its 5 closest neighbors, right? It realizes that three close ones here are green, and then 2 are red, and so therefore it's likely to be a green. Does that make sense? So it just looks around itself and is like, all right, like most here are green, so I'm probably a green as well. Okay, so that's called K nearest neighbors. Principal components analysis. So this is an unsupervised machine learning method, and it's quite cool, but you basically just project data onto a lower dimension based on the eigenvectors, right? And so you can figure out what the main axis of this data are, okay? So a lot of math in this, we won't go through it too much, but it is something that you might still see around in medical research. TSNR, so I can't actually even remember what TSNR stands for, but it's a nice graphical method for you to basically project high dimensional data into like a 2D plane, right? And then you color the types of categories it is, and then allows you to see like the different classes of things. So it could be like this is kidney cell or something, and this is like some other type of cell. Does that make sense? Okay, K-means clustering. So this is another unsupervised method. And it's basically a algorithm that basically just detects the different types of clusters you have, okay? And I won't go into like significant detail about how it works, but it's just a pretty effective way to basically find groups of things, right? So that's a cluster there, that's a cluster there, that's a cluster there, and that's a cluster there. Okay, collaborative filtering. So this is actually the algorithm behind the Netflix data set, right? And so there's a lot of math related to this, but basically it's a great thing to have if you need to suggest items based on the preference of other users, right? Or you can frame the problem in that way. So it's, for example, you know, looking at this, like Charlie likes this, he doesn't like this. You know, the question is, will he like that, right, if I recommend it? And so it basically looks to find users which are most similar to Charlie, right? So Bob in this case is quite similar to Charlie, so it's likely that he's not going to like it as well because Bob didn't like it, okay? All right, and so let's see what time it is. Maybe we can do this in real time, right? So see if you can suggest to me the best method for these type of problems. Okay, so let's run through the first one. If you want to recommend movies or songs to users, which of these would you use? Perfect. All right. Classify emails as spam or not spam. Go for it. SVM? Yep, SVM is a good choice. Okay, predict housing prices based on features like size and location. Sorry? Yeah, regression. I mean, in this case, you can also use, I think, decision trees or random forests as well. Could also help, right? Group customers based on purchasing habits. Sorry? Yeah, so K means clustering, right? Recognize handwritten digits. Sorry? Yeah, you can use deep learning. I mean, like this one, you can also use K nearest neighbors. This is just the basic ML stuff, right? And then visualize genetic data to identify patterns. T-SNR, perfect. Okay, and that's it. So that's the agenda for today. Thank you so much. And so next week, we're gonna get started on, actually, I think in the first day, we're gonna do some more PyTorch and neural network stuff, right? So I think we're planning a bit of a Kaggle neural network competition. But then later in the week, we're gonna cover word embeddings and then transformers, which form the backbone of GPT right now, right? And then on Monday and Tuesday week, we're gonna cover some more exciting stuff around transformers, right? So we're gonna hopefully boost you up quite quickly in terms of what's happening in state of the art, okay? Cool, so hopefully you have a great weekend. See ya.